Howdy, and welcome to Mean 315 lecture number 17. And welcome back from spring break. Hopefully all of you had a relaxing and enjoyable time, either just not being in school or away from College Station, wherever it may have been. And I'm excited to be back with you with thermodynamics as always. Okay, so we're going to we're in the midst of a transition again. So if you remember before spring break, we were talking about steady state open systems, and we were talking about specific devices that we commonly model as being steady state devices. Devices such as turbines and compressors, pumps, throttles, nozzles, diffusers, so on and so forth. So now we're going to switch gears and we're going to close the system, and we're going to talk about closed system analysis. And so this will let us talk about exciting things like piston cylinder arrangements. So we'll spend some time talking about that. So to begin with announcements, first of all, homework number 7 is assigned and is due on Thursday, March 20th, which of course is this coming Thursday. We had it due Thursday because I'm not in class on Tuesday, and so just to simplify when the homework is due, we'll make it due Thursday. Homework number 8 is also assigned and will be due Tuesday, March 25th. So you only have 5 days. If you wait to start homework 8 until Thursday when you submit homework 7, you'll only have 5 days to work on homework number 8. So do try to look at that beforehand, particularly before class on Thursday, since we'll be doing some example problems on Thursday. And your participation assessment for lecture number 18, Thursday, March 20th, will be graded and will be based on the information in this lecture. So make sure that you watch this lecture closely for your participation assessment on Thursday. Okay, so the other thing that I wanted to note, and I'll pass these out on Thursday, but I've had a chance to go through and read your group updates, and everyone is doing a really good job. Some of you are coming up with some creative solutions, which is great. One solution that I was surprised that I didn't see was the following. I almost invariably will see something like this in relation to a potential solution for how to generate electricity. Check out the sand in the hair. He's covered with it. I don't know where the sound is from. I didn't come up with the sound. Can you believe he used to be governor of California? There it is. Rotational energy. Shaft work. That's shaft work there. So anyway, a potential way to generate electricity back in the day. Of course, that won't work these days. Okay, so continuing on now with the lecture, with the real lecture material. Let me, I just briefly introduced where we are in the semester, what we've talked about, and we've seen this diagram before, so I'll just spend a little more time talking about it to help put into reference what we're now going to start talking about. So, of course, our top-level analysis is what we call our general thermodynamic system, and this is really, the system that could analyze any typical thermodynamic system. And we generally break that general system into two major categories, the open system and the closed system. And then, of course, open systems and closed systems can undergo two types of processes, either steady state process or a transient process. And depending on either of those two processes will dictate the governing equations that we use for each of those systems. So we've spent the last 2 weeks talking largely about open systems and largely about steady-state open systems. And we divided that into work devices, things like turbines, compressors, and pumps. And then the week before spring break, we talked about non-work devices, things like heat exchangers, boilers, condensers, mixing chambers, throttles, nozzles, and diffusers. The transient open system, we don't really study this semester. There's just not enough time to do it. And so the next category that we talk about are the closed systems. And we've already talked about steady-state closed systems. These would be things like motors and generators, where you have one form of energy coming in and the motor or the generator transforms that energy into a different type of energy leaving the control system. But there's no mass transfer, it's just energy transfer. The other type of closed system is the transient process. And the transient process is what we're now going to start talking about, the transient closed system process. And generally speaking, a transient process can be divided into two major categories. One is where the constant is, or the volume is constant during the process. And then the second is when the volume is changing during the process. And the most common device where you may have changing volume is in what is called the piston cylinder system, or the piston cylinder arrangement, or the piston cylinder device. They all mean the same thing, pistons inside of cylinders. And I'll bring an example of a piston cylinder arrangement to class on Thursday, but we'll also show some images as part of today's lecture. So we're now completing this system analysis that we've started several weeks ago, right after we, really going back to the start of the semester. We're now completing this with turning our attention toward studying the transient closed system process. Okay. So just to remind you, what the governing equations are for the transient closed system. We've already developed these early on this semester. You might remember we wrote them all out just to complete our analysis, and I said that we weren't going to do anything with them for the next several weeks as we went into open system analysis. Well, now it's time for us to return to these equations and return to this analysis of a transient closed system. So of course, if it's a closed system, you can see how I have it drawn here. Right? There's intentionally no mass transfer with the system. It's closed, so we're not transferring mass with the surroundings. But we can still have energy transfer in the form of heat transfer, and we can have energy transfer in the form of work transfer. And these energy transfers, for sure, could cause a change in energy and entropy, but just to be rigorously complete, we'll also say potentially a change in mass. Now, just to avoid any confusion at all, we're not going to have a change in mass, and I'll show that in just a moment. This is all classical analysis. We're not doing any relativistic type analysis where the mass could change as the energy of the system changes. That's the E equals mc squared equation, for example, is basically that transformation between energy and mass at relativistic scales, very large velocities up to speed of light type scales. We're not doing that here, right? We're not approaching relativistic conditions, so we don't need to concern ourselves with this dm by dt, as I'll show in just a moment. So as I said, the system is closed, so there is no mass flow term. There's not an m dot I or an m dot E. And the system is transient, so the properties of our system could change with time, right? So these d by dt terms, right? dm by dt, de by dt, ds by dt, dt by dt if it's temperature, dp by dt if it's pressure, these will all be, for the most part, not equal to zero, right? Because it's a transient process. Okay, so what do our general governing equations tell us? Well, first of all, we have conservation of mass, and again, I'm just including this to be very rigorous, but the conservation of mass says that dm by dt of the system is equal to the mass flow in minus the mass flow out. And mass flow in is 0, mass flow out is 0, so these two terms are equal to 0. So dm by dt is equal to 0, which of course we knew, right? So conservation of mass is really a trivial result. I include it just for completeness. Of course, conservation of energy is not a trivial result. We get a very important equation from our conservation of energy analysis. So conservation of energy says that the change in energy of the system is equal to the heat transfer plus the energy that flows in with the mass flow rate minus the work transfer minus the energy that flows out with the mass flow rate. Of course, m dot I and m dot E are both equal to 0, so this group of terms and this group of terms will all fall out of the equation. So when we take those out of the equation, we get that the change in energy of the system with respect to time is equal to the heat transfer rate minus the work transfer rate. Now, of course, this is a transient process, so the dE by dt term is not equal to 0. Before, when we were studying the steady state systems, this term on the left-hand side was equal to 0. But our system is not steady state, so dE by dt is not equal to 0, and this term needs to appear in our math equation. Okay, so now what we need to do is we need to analyze this differential equation, dE by dt equal to q dot minus w dot. And since for our purposes, we now know that we analyze transient processes from one state to a second state, right? The process has an initial state, which we typically call state 1, and it has a final state, which we typically call state 2. So we can integrate this differential equation through that process from state 1 to state 2. And so dE by dt from state 1 to state 2 is just E2 minus E1, the energy at state 2 minus the energy of the system at state 1. And then, of course, when we integrate q dot, we get the integrated functional form, the integrated form of heat transfer, which we write as q1 to 2. And the same is also true for the work transfer. When we integrate w dot, we get work 1 to 2, the integrated sum of all the work transfer that occurs during that process. Remember that heat transfer and work transfer are what we call path functions. So they depend on the path of integration, whereas energy is a state function or a point function, a property of a system. Therefore, it doesn't matter which path you take between state 1 to state 2, the energy at state 2 will always be the same. Whereas the heat transfer and the work transfer depend on the path that you take or the process that you take between state 1 and state 2. So if we remember that energy is defined as the internal energy of the system plus the kinetic energy of the system plus the potential energy of the system, we can impose these terms, this equation, into our first law equation, our integrated first law equation, and get that the energy at state 2, which is the internal energy of the system, plus the kinetic energy of the system, plus the potential energy of the system, minus its energy at state 1, is equal to the difference between the heat transfer that took place during that process and the work transfer that took place during that process. Now, this is a very important result. It's basically the first law equation for a transient closed system, okay? And it's going to be something which we use consistently whenever we're doing the analysis of a closed system. It's also important to note that this equation is fundamentally the same, but just appearing in a different form than the steady state first law equation that we developed for open systems. The assumptions that we use to get to this equation are different than the assumptions that we use to get to the steady state equation because they're two different processes and they're two different types of systems. One is for an open system undergoing a steady state process. This one is for a closed system undergoing a transient process. And I have a little explanation to help identify the differences between the two sets of equations in just a moment. Before we get to that, though, we can go over the second law equation. And so, of course, we start with our general second law equation, which says that the change in entropy of the system is equal to the entropy that's added due to heat transfer plus entropy added due to mass flow minus entropy that's removed due to mass flow plus any entropy that's generated. And of course, there is no mass flow, so m dot I and m dot E are both equal to 0. So this equation reduces to the following form after we integrate for the process from state 1 to state 2. So we get that the change in entropy of the system, and again, entropy is like energy, it's a state function, it's a property of a system. So you have entropy at state 2 and entropy at state 1. And so S2 minus S1 is on the left-hand side. And then this is balanced by entropy that's added to the system due to heat transfer or removed if it's negative heat transfer, plus entropy that's added due to generation, which of course this entropy generation term can only ever be positive. And so we call this the transient closed second law equation. I should also point out there's actually a small mistake in here. So again, that's an opportunity for a bonus question. When I integrated this, I imposed an assumption here that the temperature of the surroundings was constant, or that the temperature of the system was constant during this integration. And so I probably, to be quite rigorous, should not have done that. So I'll consider that a mistake, and that can serve as one of the bonus questions, or at least the bonus question during the participation assessment. So the way that this should have been written is to be rigorous, I should have just left it as the integral of delta Q over T, because I can certainly integrate the time function away, but it would have been left as the integral of delta Q over T. Okay, so as we talked about, we can compare the open system steady state equations to what we just developed as the closed system transient equations. And they're very similar, but there are some very stark differences that we need to pay attention to. The first is related to the conservation of mass. For the closed system, right, I say our system, but in this case I mean closed system because that's what we're talking about right now. Conservation of mass is meaningless, right? There is no mass flow rate, and so the mass flow rate terms will not appear in any of the closed system equations. You'll recall that the open system equations are written on a rate basis. That is, Q dot and W dot appear in the terms, whereas with the closed system equations, we write them on an integrated basis. So we don't have Q dot in the closed system equations. Instead, we'll have something like Q1 to 2 or work 1 to 2. In the case of the closed system equations, it includes the energy of the system, right? So if we go back up here, and we look at our first law equation, this collection of terms is the energy of the system. So internal energy of the system, kinetic energy of the system, right? So if this whole box here, if this whole system here were moving with some kinetic energy at one state, but then was moving at a different velocity at the second state, then this whole system would have undergone a change in kinetic energy. Before, when we did the open system steady state analysis, we assumed that if the system were moving, right, that its velocity was not changing, its kinetic energy wasn't changing, because we said that the change in energy of the system was equal to 0. That's not the same as saying that the change in kinetic energy of the flow is equal to 0. You still have the kinetic energy term inside the summation with m dot I times hi plus 1/2 vi squared. That's a different kinetic energy. That's the kinetic energy of the flow. This kinetic energy that's in this equation here, this 1/2 mv squared, is the kinetic energy of the whole system. Okay? So it's important to recognize the difference between the terms that are associated with the system versus the terms that are associated with the flow. And I haven't emphasized this before because we really haven't had an opportunity to draw a comparison, but now that we're starting to develop these equations for a closed system, we can start to recognize that there are properties related to the system. So these are properties related to the system versus properties that are related to the flow. And so if we go back up here to the general first law equation, these are the terms that remain in the steady state open system equations, but these terms here are all related to the properties of the flow, okay, as opposed to the properties of the system. Okay, so that's item number 3, right, where closed system equations include the energy of the system, hence the appearance of internal energy in the first law equation. Open system equations, however, include the energy of mass flow, hence the appearance of H in the first law equation. Okay, now another difference that's commonly found in the application of open and closed systems is the nature of the work transfer. So typically, open systems transfer mechanical energy as shaft work, right? So if we go back to our buddy Conan, he was basically putting shaft energy into the wheel of pain. Shaft work, of course, is rotating shaft that transmits torque. So again, Conan here is basically exerting a force, right? If we go back a couple of frames, Conan here is let's see if I can find a good frame here where you can see the actual, I guess maybe that's the best image there. Let's see if I can get this. So right here, right? So this is, of course, the lever that's extending from the axis of the wheel. Conan is exerting a force at some distance from the center of the wheel, so he's putting torque on this wheel, right? Torque is force times moment arm. So his position here is giving a moment arm on that wheel. Of course, had he known and he stood a little closer to the edge of the wheel, he would have had to exert less force in order to move the wheel, right? Since I'm sure that there was some resistive torque in the bearings. But anyway, it wouldn't have been as dramatic if he had done that. So I understand why he did that. That's how he won the governorship, after all. So anyway, that's the type of work transfer that we have in an open system. And of course, if we just for a moment spend a little more time talking about this shaft work, right? So we said before that the shaft power, W dot, is equal to 2 pi times the torque times the rotational speed in revolutions per second. That 2 pi converts the revolutions per second into radians per second. So if we take a look at this equation, neither torque nor rotational speed are thermodynamic properties of the system. We can write the shaft work equation that does depend on properties. And we haven't talked about this a lot. We're going to come back to this in about a week or two, where we can write the shaft work as being the negative integral of specific volume times the change in pressure, right? So again, if we think back on a turbine, which is an open steady state system, this shaft work, right, makes use or exists because there's a pressure drop across a turbine, for example. So steam comes into a turbine with a certain specific volume. That specific volume, of course, is changing through the turbine, but the steam also experiences a pressure drop. It has a higher inlet pressure than its exit pressure. And so there's a negative drop in pressure times the changing specific volume. You integrate that through the length of the turbine and negate it because it's a pressure drop, and you end up getting positive shaft work out of the turbine system. Okay. So we'll talk more about this equation a little bit later and where it comes from. But for now, what I want you to know is that in contrast to this, in contrast to shaft work, in contrast to this shaft work, which we see typically with open systems, is the closed system work transfer is typically of the form which we call boundary work. Okay, so that's what I want you to get from this discussion, is that closed system work transfer is typically of the nature called boundary work. Okay, boundary work is that which results from a moving boundary, and that moving boundary is what transfers mechanical energy. Now, it's entirely possible for open systems to have boundary work, and it's entirely possible for closed systems to have shaft work. We don't have to say that only open systems can have shaft work and only closed systems can have boundary work. That's not what I'm saying. What I'm saying is that the typical nature of closed system work transfer is boundary work, and the typical nature of open system work transfer is shaft work. Okay, so now, before I spend more time talking about boundary work, what I want to say is that we've calculated shaft work from turbines and compressors, but we've never used this equation before. We've never used shaft work is equal to the negative integral of VDP. And the reason why is because it's not very helpful for us when we do things like turbines expanding steam or compressors compressing R134A. Because this specific volume term is changing as the pressure of the steam or the pressure of the R134A is changing, and we can't easily characterize that behavior. It's dependent more on the nature of the substance than it is on the actual boundary conditions or the interactions of the system with the surroundings. Okay. So because of that, this equation has very limited use. It does have use, and we'll come back to its use later on in the semester, but that's why we never really talked about it when we did work transfer for turbines and compressors, because it has very limited use. Boundary work, on the other hand, has a very strong connection to its surroundings. It's essentially influenced by its interactions with the surroundings. And because of that, boundary work tends to be more a function of the surroundings that the system is interacting with instead of the substance that's actually within the closed system that's affecting the work transfer. Okay? We're going to explain this, so if that's not making sense just yet, just hang on and we'll get to it. Okay? So boundary work is that which results from a moving boundary that transfers mechanical energy. Okay? And there's a very, very common example of boundary work transfer. And it's what we call the piston cylinder arrangement or the piston cylinder system. A piston is basically a means to transfer work through boundary work. Okay, so what does a piston cylinder arrangement look like? Well, I've got several examples here. So this is basically where you see my mouse here. That's the piston. Okay, and you can see that it's inside what used to be a cylinder. This has been cut away to be able to illustrate what a piston cylinder arrangement looks like inside an engine. So this is basically an internal combustion engine, and there's valves up here that you can't see because of the darkness in the metal that's basically blocking its view. But you have this piston, and this piston what we call reciprocates or goes up and down inside this cylinder. And in fact, in this cylinder here, so this is a neighboring cylinder, you can in fact see that the piston is at a lower position where it's basically in its downstroke. Okay, so these pistons go up and down inside this cylinder, right? And different processes are happening inside this system, right? So the system in this case is inside the cylinder. Okay, where my mouse is where the system is. So there's the top of the system, which in the case of a internal combustion engine, we would call this the cylinder head. And then you have the cylinder walls, right? And then the bottom of the cylinder is basically the piston. So you have 1, 2, 3 stationary walls, but then a moving wall, your moving boundary. And this is where the boundary work transfer takes place. Because of this moving piston, you have boundary work that's transferred out or into the system. Okay, so you can see how exactly this works, right? So in this image here, these pistons, right? So this is the piston. It's a different type of, it's a different designed piston, but it's a piston nonetheless. And in this case here, we're not showing the pistons inside their cylinder. Instead, what I'm showing is how the moving piston transfers work out of its thermodynamic system. So you have the piston, which would form one of the walls of your system, and it's connected to a connecting rod, and which is this rod that you see here that my mouse is over. And then the connecting rod is connected to what we call a crankshaft, right? So this long horizontal shaft with a bunch of different things on it, which I'll describe in just a moment, is called a crankshaft, okay? And the connecting rod is connected to the crankshaft in an eccentric location relative to the center line of the crankshaft, right? So as I run my mouse along the crankshaft, what I'm doing is I'm running it along the center line of the crankshaft, okay? So this is the concentric axis of the crankshaft. It's what the crankshaft, it's the axis that the crankshaft rotates around, okay? So that's the crankshaft center line. And the connecting rod is connected to the crankshaft in an offset location, right? In what we would call an eccentric location. And the offset of the connecting rod's connection to the center line of the crankshaft dictates the stroke of this piston, okay? So that's what you can kind of imagine that if this connecting rod is connected very close to the center line, then the piston would have a very short stroke, right? It would only go up and down a small amount. But if the connecting rod is connected very far away from the center line of the axis, then it would have a very long stroke as the crankshaft rotates around its center line and pulls the connection of the connecting rod along an eccentric circle relative to that crankshaft. So in this case, there are 4 pistons, right? 1, 2, 3, 4. and they're all indexed or located to the crankshaft at different locations to basically help create balance within the engine, right? The other item that helps to create balance within the engine are these counterweights. So you see these big metal masses here that are connected to the crankshaft. Well, those are called counterweights, and they're basically meant to help balance this inertial mass that you have stroking up and down on the crankshaft. So you can imagine that if you didn't have these counterweights, this crankshaft would vibrate and wobble like crazy, much like a washing machine does when the load inside the washing machine becomes unbalanced and it goes into its spin cycle. So these counterbalances are used to help basically balance this inertial mass that's constantly stroking relative to the crankshaft. There's also a gear on here, and so this gear could be used, for example, to drive directly some other item that the engine needs to run. So oftentimes they drive oil pumps, for example, to help pump oil around the engine, or they might drive a water pump, or there could be some auxiliary work system that this crankshaft needs to drive as it rotates, as the engine runs. And then the other thing to note is that this little smooth metallic surface that you see here, this is basically a bearing, or a bearing surface, I should say. So this is one of the bearings that would hold the crankshaft into the block of the engine. And so there's a bearing here, there's a bearing here, there's a bearing here, and then there's another bearing on the end here. Okay, and so again, those bearings are what hold the crankshaft in place and allow it to spin freely within the block. Now, if you look real closely, you see that little hole there? Well, that's actually an oil dispensing hole. And so when the oil pump is running, oil is pressurized all through the engine, and oil is going to all different locations in the engine, including to the bearings. And there are holes that are purposefully drilled into the crankshaft, and there will be an oil inlet at one of these ends where oil is pressurized to the crankshaft to basically supply oil to all the bearings, not only your journal bearings, so these are the journal bearings that are holding the crankshaft into the block, but also into your connecting rod bearings so that you can lubricate this bearing here between the crankshaft and the connecting rod. So it's always important to make sure you have oil in your engine. So of course, piston cylinder arrangements are incredibly ubiquitous. There's not a single day that goes by probably that you don't interact with a piston cylinder arrangement in some way or another. They're used, of course, in internal combustion engines. They're used in air pumps. They're used in compressor pumps. The compressor that you have in your refrigerator, in your dorm room or your apartment or your house or wherever, any refrigerator that you touch has a piston cylinder arrangement in it because that compressor will use a piston cylinder arrangement to help pressurize the substance. So, but of course, you may also have one of these in your home, right? I mean, how incredibly useful is this? In addition to being really awesome, to have a piston coffee table. I mean, this is just totally cool. So the only thing that this coffee table is missing is a book about coffee tables. So that needs to be fixed. Okay, so anyway, now getting back to the actual thermodynamic analysis of things, like shaft work, we can develop an expression for boundary work that is a function of system properties, right? So this was the function of shaft work that is, or this is the equation of shaft work that is a function of system properties. We can do the same thing with boundary work, right? We can develop an equation that's a function of system properties. So to do this, we start with our basic definition of work transfer, where work transfer is the integral of force times displacement. You all remember this from Physics 218 or from physics in high school, whatever the case may be, where force, of course, is F and dx is displacement. Okay, well, when we think about a piston cylinder arrangement, our force is basically pressure of the system, and our displacement is basically the motion of the piston up and down. Well, how can we take those two pieces of information and translate them into properties that we commonly think about? Well, we have here our piston cylinder arrangement, right? So this is how we typically draw our piston cylinder arrangement. So this is a side view. So this is the piston here, and this is the cylinder. And the system that's bound by the piston and the cylinder is our control system. So this is our control system here. We have our connecting rod. That's what this little set of lines are meant to represent, right? And I don't draw it all the way down to the crankshaft, but that moving piston is what gives us our work transfer. And we, of course, recognize that the piston is moving up and down inside the cylinder, so we can have some position, which we identify as X, that positions this piston's location at any moment in time. If we also take a top view, right, so I meant to write top up here, and I forgot to do that, but if we take a top view, then we can basically, I wonder if I can, well, I won't mess around. So if we do a top view, then this dashed line basically represents the piston, right? And it has a diameter, and the cylinder is circular, right? So we now have a diameter, a circular area, that and a piston that's moving through some longitudinal distance. By the motion of this piston stroking up and down, it sweeps out a volume. Okay, so our volume is going to actually become our displacement. So at any moment in time, the volume of the system is just the area of the piston, right? Pi over 4 times diameter squared times the piston's location, x, okay? And if we consider the fact that the piston is moving up and down, x is always changing, but the area of the piston is basically constant. We're always dealing with circular pistons. I've never seen a non-circular piston. And so the area of that piston is constant. So the differential change in volume is dV, which is equal to the area of the piston times the change in x, dx, which is equal to pi over 4 d squared times dx. So we can solve directly for dx because that's what we have in our boundary work equation, and get that dx is equal to dV divided by the area of the piston. We also recognize that the system is exerting a pressure on the piston and the cylinder, and that pressure is equal to the force divided by the area of the piston, right? So force is equal to pressure times area of the piston. So we have an expression for dx, and we have an expression for force. And so our work term now becomes the integral of f dx, which is the equal to the integral of pressure times area of the piston, this is our force term, times dV divided by the area of the piston, this is our dx term. So this is now equal to the integral of P dV times pressure times the change in volume. So our boundary work that we'll use this semester is, or our boundary work transfer equation is work 1 to 2 is equal to the integral from 1 to 2 of pressure times the change in volume, dV. Okay, now we're dealing with a closed system, so the mass in the closed system is, for all intents and purposes, constant. So we can write the specific work transfer, just divide each term by the mass, right? We divide the left-hand side by mass and the right-hand side by mass, and we get little work 1 to 2, this is what we call the specific work transfer, is equal to pressure times the differential change in the specific volume, so d little v. Okay, so now that we have this this equation, right, these work transfer equations, we can now explore the possibility of evaluating these for a certain number of specific cases, right? So I just want to close the loop now on our discussion between shaft work and boundary work. Notice that the boundary work transfer is the integral of pressure times change in volume. Shaft work transfer, however, is negative integral of volume times change in pressure. Okay, do you see the difference? Boundary work doesn't have the minus sign. Boundary work has pressure as the functional term, and the differential change is with respect to volume, not with respect to pressure. Okay, so make sure that you recognize the difference between the shaft work equation and the boundary work equation. Okay. Now before we said that it's not easy for us to evaluate the shaft work equation because we can't easily come up with a functional relationship between specific volume and pressure to be able to integrate negative VDP. That's not true for boundary work though. In the case of boundary work, because there's this interaction with the surroundings, there's this idea of the boundary moving through the surroundings, we can relate pressure of the system to the system's interaction with the surroundings. Okay, so let's go through several cases where we can do this, and how we can evaluate this equation will become clear. Okay, so the first case that we want to evaluate is that for the constant volume process. So in the case of the constant volume process, the change in volume, of course, is equal to 0. And we see right away that a constant volume process does not have any boundary work, right? So work is equal to the integral of pressure times change in volume. There is no change in volume. dV is equal to 0. So if dV is equal to 0, then the work transfer is equal to 0. Okay? So in other words, the system volume is constant. It's not interacting with the surroundings at all. The boundary is not interacting with the surroundings at all because the boundary is not moving, right? It's a constant volume system. And so there's no work transfer in that case. So common examples of a constant volume process are if you see that you're dealing with a rigid tank, for example, or if you're dealing with a rigid vessel. These are constant volume processes. Also, if a piston is locked in place, okay, that also would be a constant volume process. If the piston is locked in place, then the piston can't move up or down, right? It's held stationary during that constant volume process. And so there's no work transfer because the piston's not moving. There's no boundary work. Okay, now the next case to evaluate allows us to now recognize how a system with a moving boundary is influenced by its surroundings, okay? And that is in the case of the constant pressure process. So if we have a process where the pressure remains constant, we can evaluate the boundary work equation pretty easily, right? Work is equal to the integral of pressure times change in volume. And because pressure is constant, that comes out of the integration. So we get pressure times the integral of dV. Well, the integral of dV is just the change in volume. And so the boundary work equation for a constant pressure process becomes pressure times volume at state 2 minus the volume at state 1. Okay, so I put a box around this because you'll use this equation a lot because we often encounter constant pressure processes in our thermodynamic analysis. So this is straightforward, right? The evaluation of constant pressure work equation is straightforward. But what can often be challenging is identifying when a constant pressure process takes place, okay? And this is where we have to think about how the system interacts with the surroundings. So let's suppose you have two piston cylinder systems that are identical to each other, okay? The cylinder is the same size, the piston is the same mass, they're in the same atmospheric pressure area, okay? In fact, they could be right next to each other, so they have the same atmospheric pressure. They're identical to each other except for one thing, okay? System 1 has one mass on top of the piston, which has a mass of what we call M1. System 2 has two masses, so you can think of these as weights, okay? Has two masses on top of the piston, one that is the same mass as the one mass on system 1, M1, but then a second mass which has a mass of M2, okay? So, what are the pressures of each system? Well, if we evaluate the pressure of system 1, that's simply the sum of forces, right, acting on system 1 divided by the area of the piston, right? In other words, this piston is floating on top of whatever is inside this system. Let's say it's air, just to simplify the example. So you have air that's trapped inside your cylinder with a piston on top, and so that piston is floating on top of the air. Well, the question is, what's the pressure of that air? Well, since the piston is floating, there's a balance of forces. The pressure of the air is balancing the downward forces that are pushing down on that air. Okay? So the system pressure is the sum of forces divided by the area of the piston. Well, what are these pressure forces? We have atmospheric pressure. Okay? We have the weight of the piston, the pressure imposed by the weight of the piston, which is of course the mass of the piston times gravity divided by the area of the piston. And then we have the pressure imposed by the weight of mass 1, the mass of 1 times gravity divided by the area of the piston. Okay, so that all makes sense. Now, what is the pressure of system 2? Well, again, we can assume that there's air inside this system, right? There's this cushion of air, and the piston is pushing down on that cushion of air. But now, in addition to the atmospheric pressure and the weight of the piston and the weight of mass 1, there's also the weight of mass 2. And so this piston with the two masses on top are pushing down on the air inside system 2 harder than mass 1 and the mass of the piston are pushing down in the air in system number 1. So we can see right away that the pressure of system 2 is greater than the pressure of system 1 by this additional mass M2 that's on top of the piston. Okay? So you can now see how the surroundings, right? So this is our system, but the piston and the mass and the atmospheric pressure are all the surroundings. So the pressure of the system is being influenced, it's basically being controlled by the surroundings. Okay? And so this is one example of where we can see the surroundings affecting the pressure of the system. Okay? So clearly the pressure of system 2 is greater than the pressure of system 1, right? Because system 2 includes this additional mass term. Okay? And what it allows us to do is make the observation that the pressure of the system is a function of the external forces on the piston. That is, it's a function of the surroundings interaction on the system. Okay? Now we can carry this example a little further, and we can suppose that system 1 undergoes a process where M1 is removed. So in this example, forget about system 2 now. Okay, we're only thinking about system 1. And in this example, what we do is we have this piston with M1, right? And then in process 1 to 2, what we do is we remove M1, okay? And the question becomes, what is the pressure of the system at state 2 relative to the pressure of the system at state 1? Well, we took this mass off the piston, right? So if this is my piston and I have a mass on top, right? And then I pull that mass off, well, the piston will rise up, right? And because the air pressure was balancing that additional force of the mass, and there now needs to be a new equilibrium of pressure balances, and so the air pressure will push the piston up a little bit, and the pressure of the air, the pressure of the system, will decrease because now there's just the mass of the piston and the atmospheric pressure that's imposing on the system. Okay? So P2 of the system will be less than P1 of the system since the external force on the piston changed during the process. That is, we removed M1. Okay? Let me just carry the example one step further. Okay? So when does pressure stay constant, right? Since we did the analysis for a constant pressure process, and neither of these examples are for the same pressure yet. So when does the pressure of the system stay constant? Well, the pressure of the system stays constant whenever the external forces on the system are constant, right? Whenever the external forces do not change, then the pressure of the system will not change. Okay, so let's consider this example here now. So we have a piston cylinder arrangement, and initially the piston is down here at state 1, and just to complete the example, we're also going to say that there's this mass, M1, sitting on top of the piston. Now, what we do is we add thermal energy to the system in the process of state 1 to state 2, right? So as the system goes from state 1, or the system goes from state 1 to state 2, because we add thermal energy to the system during that process. So as the thermal energy is being added, of course, the piston is going to lift up, right? You're making the temperature of the system hotter. Maybe it's air. Let's suppose, just for simplicity, that it's air. So as we add the thermal energy to the system, the piston will rise, right, inside the cylinder. And the question is, well, what does the pressure do? Is the pressure when the piston is up here at state 2 higher, lower, or the same as the pressure at state 1? Well, in fact, the pressure is exactly the same. Even though the volume is larger, right, the pressure of the system stays constant. Why did the pressure of the system stay constant? Because the mass didn't change, right? The external forces on the system didn't change. All we did was we lifted the piston up, but we lifted that piston up by adding thermal energy to the system. So the temperature of the system is greater at state 2 than at state 1. The volume of the system obviously would be greater at state 2 than at state 1, but the pressure is exactly the same because the external forces did not change. Okay? So you'll get some practice on homework number 8 to be able to play with constant pressure processes, but it's always important to recognize that if the external forces on the system don't change, then the pressure of the system will remain constant. Okay, the next type of process that we can experience with a piston cylinder arrangement is what we call a linear pressure change. And this is where basically there's a linear relationship between the forces on the piston and the displacement of the piston. And of course, that would commonly happen if there was a spring attached to the piston, as is shown in the diagram here, right? So if the piston moves up, then the spring pushes or has a downforce on the piston, so that would increase the pressure of the system. Or if the piston were to fall down, now the spring is exerting a negative force on the face of the piston, and so the pressure inside the system would be lower than in the relaxed state. So of course, you know from physics that the force of the spring is Ks times the displacement of the spring, which is usually labeled as x. And we could integrate this, and you know, you probably remember from physics, you could calculate the work of the spring, right, which is just the integral of Ks x dx, or Ks x squared over 2. So this is still true for a linear spring attached to a thermodynamic system, but we can also calculate the work thermodynamically by evaluating the pressure-volume relationship of the system. And in fact, they would be exactly equal to each other. And so we can say that the work is equal to the integral of P dV, right? And remember that the integral of something is the area under the function that you're integrating, right? So because there's a linear relationship between pressure and volume, or I should say there's a linear relationship between the force on the piston and its displacement, which necessarily means that there's a linear relationship between the pressure of the system and the volume of the system. And so if our system were to start off at state 1 and go to state 2, then that would be a linear pressure rise as the volume increased, right? And so this is our pressure volume function that we integrate in our work equation, where work is the integral of P dV. And since the integral of a function is the area under that function, we can say that this area under this line between state 1 to state 2 is in fact the area, or is in fact the work transfer of a piston cylinder arrangement undergoing a linear pressure volume process change, linear pressure volume change. So to calculate the work transfer of a linear spring on a thermodynamic system, it's usually easier to just calculate the area under this curve. And so we can do that very easily. This is just the area of a trapezoid, right? The area of a rectangle plus the area of a triangle. And so I go through all the algebra here, which I'm not going to go through in great detail for the video. But basically what it comes down to is that the work associated with a linear pressure-volume relationship is 1/2 times the sum of the pressures times the difference in the volumes. Okay, and so again, I put a box around this to have that be a handy reference for you. But whenever you have a linear spring attached to a piston cylinder arrangement, you will have linear work transfer, and you can use this equation to calculate that work transfer term. Okay, the last process change or pressure change that we'll evaluate is probably the most important one to know. Okay, it's what we call the polytropic pressure change or the polytropic process. Why is this one so important? Because if we look at examples like this, where we have this piston cylinder arrangement, this, because of the interaction with the crankshaft, the motion of this piston inside the cylinder, the volume that it sweeps out, and the pressure that it causes the system to have, takes on the form of a polytropic relationship, right? So we talked about polytropic processes before, and of course a polytropic process is one that's characterized by pressure times volume raised to the polytropic index n, and this is all equal to a constant, okay? So piston cylinder arrangements in internal combustion engines, for example, follow this form. Follow the form of PV to the N is equal to a constant. If you trace out the pressure-volume relationship, this is what it looks like on a pressure-volume diagram. It follows this mathematical form. Okay, so that's why we talk about polytropic processes so much in this class. It's because it's such a ubiquitous process, because the piston-cylinder arrangement is such a ubiquitous system. Okay, so we've studied polytropic processes before. And we can, of course, recognize that for a we typically write the polytropic process as being P little v to the n is equal to a constant. But in the case of a closed system where the mass is constant, we can also write this as P big V to the n is equal to a constant. Okay, of course, the constant would be different, but you can still use this same functional form. So if we have a system that's undergoing a polytropic process from state 1 to state 2, we of course write P1 V1 to the n is equal to P2 V2 to the n, right? And so what that means is that we know the functional relationship between pressure and specific volume. Specifically, we can use, say, this form here and write that pressure is equal to constant times specific volume raised to the negative n. Okay? So we can take this relationship for pressure and drop that into our work transfer equation. So work transfer is the integral of pressure times the change in volume. Pressure for a polytropic process is constant times specific volume raised to the minus n. And so we can then integrate constant volume to the negative n dv. Okay, and we can integrate this for the case where n does not equal 1. This is basically the general case because n will rarely equal 1. And when we do that, we basically get that work transfer is constant times v to the 1 minus n divided by 1 minus n evaluated between states 1 and 2. Now, if you refer up here, constant is equal to P1 V1 to the n, and it's also equal to P2 V2 to the n. So we can say that when we evaluate this between states 2 and 1, or between 1 and 2, we can write P2 V2 to the n, that's the constant, times V2 to the 1 minus n divided by 1 minus n, minus the evaluation at state 1, P1 V1 to the n, this is the constant, times V1 to the 1 minus n divided by 1 minus n. Well, of course, the v to the n's cancel with the v to the minus n's, and what we're left with is the following equation, which is that the work transfer is equal to P2 V2 minus P1 V1 all divided by 1 minus n. Okay? And again, I put a box around this equation because this is a very important equation, one that will be used regularly in our closed system analyses going forward. Okay, well, what happens though if n does equal 1, right? What happens if we have this special case where n is equal to 1? Well, in this case, we have PV to the 1, right? So n is equal to 1, so it's just PV is equal to a constant, which we can say is P equals constant times V to the minus 1. And we can go through the mathematics again to integrate that and basically get that the work transfer for the case when n equals 1 is just PV times the natural log of V2 over V1. And so what we have in the box here. Okay, so does this ever happen? When does this happen? When does n equal 1? Well, it does happen occasionally. It's a specific case, but it happens actually with an ideal gas, right? So if you think about an ideal gas undergoing a constant temperature process, you have PV is equal to RT. And if temperature is constant, then P1 V1 is equal to RT1 equals RT2, which equals P2 V2. And so you have P1 V1 equals P2 V2, where n is equal to 1, right? So we can then say that in this special case, if we have an ideal gas undergoing a constant temperature process, we can write that work transfer is RT, which is the same as PV, times the natural log of V2 over V1. And you could evaluate RT because temperature would be the same at state 1 as it is at state 2. Or if you wanted to use this form, then you would use P1 V1 or P2 V2. It doesn't matter because they're equal to each other. So what I have in this box here, of course, is the polytropic work equation of an ideal gas undergoing a constant temperature process where n is equal to 1. Okay, so that's it. That's all that I have for you for lecture number 18. Be sure to be prepared for the participation assessment on Thursday, which will be graded. And be sure that homework number 7 is ready to be handed in on Thursday. And be sure to look at homework number 8. You'll actually be able to do all of homework number 8 based on this lecture. And we'll just review this and go over some example problems with lecture number 18. Okay, I hope that you all have a good day, and I'll see you on Thursday. Send me an email if you have any questions.